Hi everybody, this is Mr. Anderson doing some notes today on experiments and observational studies. Before I get started, I just wanted to remind you that this is an educational video, which means you are welcome to pause and replay this as many times as you need. I highly recommend, as I'm going through these notes, just pausing the video to copy anything down that you want to copy down, because I will be talking at the same time. And a lot of times it's hard to write and listen at the same time. So I would just pause either after I'm done talking and then write it down, or writing it down before I start talking and then just listening. Okay, just a thing that I suggest. Anyway, so section 4.2, experiments and observational studies. The first thing we're talking about is the difference between observational studies and experiments. There's some different vocabulary for each, and it is very important to know the difference in real life, because in real life you will see observational studies and you will see experiments, and knowing the difference between the two is very, very, very important, because experiments can show cause-effect relationships and observational studies rarely can do that. So experiments are always better to do, it's just sometimes they're not ethically able to be done. So they have to do observational studies. So what are these things? Here we go. An observational study observes and collects data without imposing treatments. Treatments is basically just anything you are doing to people or whatever it is you are studying. It's like, here they are, now we're going to do something to them, or we're going to not do something to them because they're a control. But in an observational study, you're not doing that. You are just looking at these things or these people, and you are jotting down notes about them. You're not physically doing anything to them, as opposed to, an experimental study. A retrospective study. So retro just means, older or back in the day. It uses historical data for an observational study. So once again, you can't exactly impose treatments on something that already happened. So you're just using old data to do an observational study. So sometimes if you're doing things that are like, comparing things from 50 years ago to now, you have to use old data. Prospective study then is just something that's happening right now. So if you're doing a prospective study, that just means you're collecting data right now as it's going on. Like even in schools, there's lots of prospective studies that are observational studies. They'll say, hey, look, some students are learning this way, other students are learning this way. Let's compare which type of way is better for learning. So that's an observational study, and it's prospective because they're just observing at the same time as they're collecting the data. Response variable, it's the variable that is measured, as well as the explanatory variable is what we are interested in determining an effect of. Oops. Boom, give that a second. So, in experiments, you usually like to have a cause-effect relationship, in which case the explanatory, you're probably used to saying the explanatory is like the y variable. It's what you're trying to measure. And that's what it is. You're interested. First of all, if you're doing a study, you better be interested in it. You don't want to do boring studies because they cost money. And you want to determine the effect on the response. So you're using this and you're saying, hey, maybe it's going to cause this to happen. Confounding is a very, very, very important thing to know. Here we go. Okay. Confounding is a variable that has a causative effect. So this is something that is causative. It's not maybe, but it is. So it's a variable that is a causative effect on the response variable, but not on the explanatory. Keep in mind, this variable, the variable we're talking about, is not one of these two. These are the ones we're looking at. We're looking at the response and we're seeing the explanatory, but the confounding is a variable that's kind of in between them. It's an in-between step that's saying, well, these are related and it's causing something to happen here, but it's not something we anticipated ahead of time. So the causative effect is on the explanatory, but not the response. I'll give you an example in a minute. But due to the method of the experiment or study, you can't separate those effects. So one of the examples that I'll have on here is basically, if you were to make a chart and you were to say the damage caused by a fire. and you were to compare that with the number of firefighters on the scene. If you think about it, then if you have a lot of damage going on, they probably sent a lot of firefighters. But, if they only sent 2 people, that means it was probably a small fire, so there wasn't a lot of damage. And if you were to plot this, you would probably see something like that, where if there is a huge fire, you would send a lot of firefighters, and the damage would be huge, right? That makes sense. Big old wildfires, like a lot of damage, and you have a lot of firefighters. But that's not saying that having lots of firefighters causes them to have damage. It's not like, if you send 10 more firefighters, all of a sudden the fire is going to be bigger. That does not make sense. That is not what's going on. So the number of firefighters does not cause damage. What's causing the damage is the fire. Woo! So the fire is what we're talking about here with confounding. It's how big the fire is. If you have a big fire, then there's going to be a lot of damage, right? This fire is going to cause the damage. But fire does not cause firefighters, right? If you have a big fire, that is not going to make more firefighters show up. Now, there will be more firefighters. If they are well funded enough, they will send more firefighters, but the fire is not causing them to come. It is not implying that they have to come. It's just they're going to because that's what makes sense. You could just be understaffed, in which case there's a huge fire, but you're still only going to send that one person because everyone else was out on sick leave, right? It's possible. This is not causing, but it is causing that. It is impossible for a bigger fire to not cause more damage. So it has a causation on one of them, but not the other. It's also known as a lurking variable. Looks like I wrote it down there. Lurking variable is just something where it's not a cause effect because of something in between that you weren't looking at immediately that's actually going to be causing it, or might be causing it. You technically don't know because that's not what you're studying at the moment. Okay, there we go. Experiment. An experiment, this is not an observational study. An experiment imposes some treatment on subjects to measure an effect on some response variable. So you have people and you are going to do something to them. Maybe you are giving them a drug. Maybe you are having them do something specific. But a treatment is saying that you are making them do something or doing something to them. So they have to be volunteers, basically, if they're people. That is an experiment. And a placebo is something you use in experiments. It is, you've probably heard about it if you took psychology. It's a dummy treatment intended to mimic explanatory variable. But it has 0 level. That's the way I like to think about it. It's a 0 level. Whatever the treatment is, if you give them 0 treatment, it's a placebo. They'll call it a sugar pill. If you know sugar pills, if they are testing drugs, they'll give someone a drug and they'll give the other people a placebo, a sugar pill. That way, both people are taking something, so they're only measuring whether it's the drug that had an effect rather than taking something. Because some people will give their kids a little tiny vitamin and say, hey, look, this is going to make you feel better. And, vitamins do help you a little bit, but at the end of the day, it's one of those, kissing a boo-boo. Kissing a boo-boo doesn't actually make the blood stop, but it makes little children feel better. So placebos are kind of like that. Is it psychological, just taking something makes you feel better, or is it actually what you're taking? So yeah, it's a dummy treatment. It's not actually a treatment. You still treat it as one though, but it has 0 level of whatever it is you're doing. So here we go. I think I'm gonna switch over to a blank copy for this example. In a recent study of about 13,900 college freshmen, a researcher found that the more time students spent drinking alcohol, the lower their grade point average. Explain how confounding makes it unreasonable to conclude that spending more time drinking causes a decrease in GPA for college freshmen. So I'm going to draw something that's not necessary, but it just helps me kind of grasp what's going on. What they're saying is, to explain how it's unreasonable to conclude that time drinking causes decrease. So time drinking causes GPA. So what they're saying is that if you drink a lot, you're supposed to have a low GPA, and if you're drinking a few, you would have a high GPA. That's what they're saying is not the case, but that's what they're saying is, what they found. The lower their grade point average, the more that they were drinking. So they're saying, how does confounding make it unreasonable to assume that drinking causes GPA? So if you think about it for a bit, it should make sense that, like, if you have this super intelligent person who's very driven, they study all the time, that if you make them drink alcohol every now and then, it's not going to exactly cause them to lower their GPA. Because they'll still be driven, they'll still be studying. So it's like, well, what is the in-between kind of that might be going on? Why is it that drinking might somehow be associated with GPA? And there's a couple of different things you can write about that. One of the things I thought of was that, you're not in college now, so you might not know this, but people tend to go drinking at night. And if you go drinking at night, you know what you're not doing? Studying. If you're out drinking, that means you are not studying. So how about that? We can do studying is a confounding variable. If you spend time studying, at night, then you're not out drinking. And that is a confounding thing, right? Drinking and GPA, none of those things say studying in them. But studying does help your GPA, correct? Studying. If you study, you will have a higher GPA. And if you're studying, that means you're not drinking. So it is affecting GPA, but it's, not explicitly said. So that is confounding. Confounding is those lurking variables. It's things that you kind of have to see the in-betweens. Okay. Next up. Observational studies and experiments. In each of the following settings, identify the explanatory and response variables. Then determine whether each is an experiment or observational. Explain your reasoning. So these should be pretty short. Okay. A recent Harvard study concluded that people who drink coffee tend to live longer than those who don't drink coffee. The study followed more than 20,000 nurses and doctors over a 30-year period, giving them frequent questionnaires to answer about their coffee habits. Researchers found that people who drank 3 to 5 cups of coffee a day had a mortality rate during the study that's 50% lower than those who did not. Okay, so first of all, it says to identify explanatory and response variables. And in the next part, it says determine whether it is an experiment or observational. All right. So explanatory and response. So explanatory is basically what they are doing, and then response is what you are measuring afterwards. So it looks like they are drinking coffee, correct? They are drinking coffee, and when they drink coffee, they are then measuring the mortality rate. So people drank coffee or they didn't. That is this. That is 2 words, coffee drank. Okay, so they drank coffee or they didn't drink coffee. That is the explanatory. And the response is the mortality rate. That is what they measured afterwards. Sweet. Boom, boom. Okay, is it an experiment or an observational study? To do that, all you have to do is ask yourself, were treatments given by the researchers? Question mark. And it is just that. In order to be an experimental design, you have to physically go up to these people and force coffee down their throats. That's what you would have to do. I'm not exaggerating. You would have to go up to these people. You would say, here's coffee, drink it now. They did not do that. It said they followed more than 20,000 nurses and then gave them questionnaires. They're observing what is happening. They are not making them drink this coffee. They're just noticing that these people are drinking coffee. So this is definitely going to be an observational study. And it's really just as simple as saying no treatments were given to the subjects. Boom. Sweet. Okay, the next part, recent study. By the way, I would pause this and try the next one. Okay. A recent study investigated the potential benefits of caffeine on athletic performance. Volunteers were randomly assigned to compete in a 10-kilometer bike ride after consuming caffeine. Woo! Meanwhile, the others were given the placebo. Let's see. Consuming caffeine and the others had a placebo. Gotcha. The average time to complete the 10-kilometer bike ride was faster for subjects who were given caffeine. So it looks like they were given caffeine or a placebo. That means that's going to have to be the explanatory. Caffeine or not. Then response is what we're measuring afterwards, which I think was the race. Yeah, average time to complete the race. Time to complete 10-kilometer race. That's what they measure afterwards. As for the observational study versus experimental, they are physically making these people have caffeine, right? They're randomly selected to compete in this thing. Yeah. After consuming caffeine and others took it. So they were choosing that. Whether they got the caffeine or not, and they gave the rest of them placebos. So this one is experimental. Treatments were assigned. That was caffeine or no? I think I spelled caffeine right. Whatever. All right, that's it. Onwards to notes again. We're at almost 20 minutes. So here we go, just some more vocab. Experimental units or subjects are individuals or things on which the experiment is conducted. We use this vocabulary word a lot. You'll see me write EU a lot. That means experimental units. It's just the individuals we're talking about. Most of the time they will be people in our examples. The experimental units are the people, whatever you're studying. The subjects, same thing. They are the individuals or things which the experiment is conducted. It's just, I'll just put it this way. When you are doing a study, you are supposed to remove all thoughts and feelings from what's going on. The whole ethics kind of question, ethics decisions happen before a study starts, but not during. So once you get into a study, you start thinking about them as experimental units, not people. Because as soon as you start to have feelings about people, all of a sudden those feelings get in the way of the science. So the whole, ethics part of should we be doing this feely-wheely kind of stuff happens before, but as soon as it's getting into you don't want to bias it because you have feelings for people and this person looks like they're doing better than the other person when really they're not. Okay. A treatment, the level of factors given to a group of subjects. So there are different levels, as you'll see, but there's multiple treatments you'll see through examples, but different levels. That's the one down here. I'll just put them all in here and tell you how they all connect to each other. So treatment is the level of factors. That includes 0. You could have a 0 factor. So if you're doing nothing to something, that is still a treatment. So it's the factors given to the group of subjects, where factors are the explanatory variable or variables. These are changed by those conducting the experiment. So whatever you are doing, that is called a factor. If you are giving them caffeine, that is a factor. The treatment is them getting caffeine or them not getting caffeine. You could also do double caffeine. A factor would be caffeine. The treatment would be getting double caffeine, regular caffeine, or no caffeine. So there'd be 3 treatments, but only 1 factor. That's an example. The level would then be what I said, the value of it. So the 2 levels or the 3 levels would be double, regular, and none. So example, amount. How many are there going to be? Let's do that here. So how are factors, levels, and treatments related? I kind of talked about this already. The amount of treatments is every combination of factors and levels. Because if you think about it, if there's 3 levels of, I don't know. I think this example is just probably the easiest to do, so I'm just going to show it. Suppose you were trying to see how fast something was growing. There are 2 big things that talk about when you are trying to see how things are growing. The amount of sunlight it gets and the amount of water it gets. So if you are trying to grow a plant, you could give it 3 levels of sunlight and 5 different levels of water. Right? And you would want to see how they kind of interact with each other. And that's saying the amount of treatments is every combination thereof. So you could have low level, and then you'd have to give them all 5 different levels of water. Then you would have medium level of sunlight, and then you'd have to do all 5 different levels of water. Then you'd have more sunlight, and you'd have to do all 5 again. So it's every single combination. The ones I gave here were like 3 levels of sunlight. Let's say it was 6, 10, or 14 hours. And the 5 different, boom, there we go, levels of water were twice a day, once a day you water them only once every 2 days, water them once only 3 days, or never water them at all. So the amount of treatments would be every single combination, right? There are 2 factors. The 2 factors are sunlight and water. Sunlight has 3 levels. The levels are 6, 10, and 14 hours. Water has 5 levels. Twice a day, once every 2 days, once every 3 days, and never. So this factor has 5 levels. This factor has 3 levels. And how many treatments there are is every single combination. It's the number of levels times the number of factors. So in this case, there were 3 levels, there are 5 levels, makes 15 total treatments. This one, 1, 2, 3, 4, 5. This one, 1, 2, 3, 4, 5. This one, 1, 2, 3, 4, 5. Total of 15 different treatments, every single combination. And this video is at almost 25 minutes. So I'm going to pause it there, and we'll come back next time to do... No, I changed my mind. We'll do this one example and we'll call it a day. Okay. Example. Probably don't want to use this one. And now there's going to be an announcement on the big announcements because I'm doing this after school, and this is good times.
Thank you.
All right. Experiments with multiple explanatory variables. Does adding fertilizer affect the productivity of tomato plants? I'd hope so, or that'd be pretty crappy fertilizer. How about the amount of water given to plants? To answer these questions, a gardener plants, oh boy, let me get my highlighter. Plants 24 similar tomatoes in identical plots in his greenhouse. He will add fertilizer to the soil of half the plots. Okay, fertilizer to half. Also, he will water 8 of the plants with a half gallon. Oh boy, okay. 8 with a half gallon, 8 with a 1 gallon, and the other 8 with 1.5 gallons of water per day. At the end of 3 months, he'll record the total weight of tomatoes produced by each plant. So listing the factors in the experiment and the numbers of levels for each. So the factors, it looks like I highlighted them. The factors are going to be the fertilizer and the water, because those are the 2 things that are going into it. He's watering them and he's giving them fertilizer. So those are the 2 factors. So fertilizer, that's 1. And the other one is water level. Fertilizer, those are the factors. Number of levels, let's see, fertilizer. He will add fertilizer to half of them. And that's all it says. Which means either they will have some fertilizer or they will have none. Either they had fertilizer or they didn't. So there were only 2 levels. Water level, it looked like I highlighted 3 different things. So there were 3 levels. There's the 0.5 gallon, there was the 1 gallon, and then there was the 1.5 gallon. So those are 3 levels. And the 2 levels right there. Okay, if the researcher used every possible combination to form the treatments, how many treatments were included in the experiment? That's just the simple arithmetic. There was 2 over here with fertilizer. There's 3 over here with the water level, which makes a total of 6. Easy peasy, right? It'll be some, 1, 2, 3, none, 1, 2, 3. C, list all the treatments, exactly what I just did. So we're going to have some. I'm just going to use the letter S for some and N for none because I'm lazy. So you'll have some fertilizer with the 0.5 gallon. You'll have some and the 1 gallon. You'll have some and the 1.5 gallon. Then you'll have none and the 0.5 gallon. You'll have none and the 1 gallon. You'll have none and the 1.5 gallon. That's every single combination of these treatments and levels. Okay. I think whoops, too much. All right, as I said, we're going to pause there. So thanks for watching.